So in this video we're going to introduce the idea of parametric equations. So to kind of get at this idea, here's an example where an object has been projected into the air at a 45-degree angle with an initial velocity of 40 feet per second. And if you work this out, the rectangular equation, the equation in terms of x and y, that describes the flight path of the object that's projected is given by this equation right here. So y equals negative x squared over 50 plus x. So a downward opening parabola. And down here I have the graph of it, but I've restrained it from the time it leaves the ground, so I haven't drawn in the part where that starts before the beginning of flight. And over here would represent where we hit the ground, so I haven't drawn in any of the parabola below that point because it wouldn't make sense to do that. So I've only drawn the part of this parabola that corresponds to the object being in the air after it's projected. So this is the rectangular representation of the ball's flight. So we have a vertical distance here, so the vertical distance is here, and this axis is giving us the horizontal distance or horizontal position of the object that's been thrown, tossed, or otherwise projected. So the problem with a rectangular representation of this situation is it tells you where the object is in terms of the x and the y coordinates. If you plug in a value for x, like if I plug in 20 square root of 2 for x, then and I work through and simplify it, then I get the y coordinate that corresponds to it. So this representation gives me the position of the ball, but it loses the information about time. It doesn't tell me when the ball is at a particular position. So this is a significant deficiency in the rectangular representation, and this is why we introduced the idea of parametric equations. So parametric equations. And parametric equations simply is where we parameterize the x and the y coordinates in terms of some third parameter. In this case, the third parameter is time, represented by t, although we don't have to introduce a time parameter. Any third parameter that controls x and y over some defined domain will give us a parametric representation. So the idea is, by parameterizing x, by saying, hey, I want to know where x is as a function of time and where y is as a function of time. In other words, we know the x and the y coordinate on the graph based on time. This is a parametric representation. So x has been parameterized with t, and the y position has been parameterized with variable t. So the nice thing about this representation, for example, is if I plug in time equal to 1, I see automatically that at time equal 1, or 1 second into my flight, I'm at the position 20 square root of 2 feet. And we plug in 1 for the y variable, and this simplifies to negative 16 plus 20 square root of 2 feet. Whereas with the rectangular, I would have had to have plugged the value for x in, and I wouldn't have any idea that I was at this position when time was equal to 1. So the parametric representation is nice when we're modeling things with positions with respect to time. It's nice to parameterize with respect to time. There's also some relations that are either difficult or impossible to model in rectangular coordinates that have simple parametric representations. So the next slide, we just kind of formalize the definition of a plane curve. So here's the formal definition. If f of t and g of t are continuous functions, so no discontinuities, so continuous functions of time where time is running over some interval, so we have an interval over which we have continuous functions, then x equals f of t and y equals g of t are parametric equations, and t is called the parameter. So in the previous slide, this right here was playing the role of f of t, and this equation right here is playing the role of g of t in the definition slide. So as t runs over its interval, X and Y take on values, and if you graph the values that X and Y take on as t runs over the entire interval, the graph that you get in conjunction with the parametric equations define a plane curve. And in calculus, it is common to use an uppercase C to denote a plane curve. So in the previous example, the graph, as time ran over the interval that started the flight of the object and ended the flight of the object when the object hits the ground, as time runs over that interval, the time interval during which the object is in the air, we have a curve C that is laid out, and the graph together with the parametric equations that generate the graph, those together give you the plane curve. So that's just a basic introduction to parametric equations. The next video will look at how to graph them using GeoGebra.